really interesting pieces of information exist in the table. If you spend any time at all, you'll notice that some of the symbols don't really line up with the names. By now, you'll kind of have read and watched a few videos about how the periodic table was developed by numerous people and then culminated with the work of Dmitri Mendeleev into what we see today. It contains all the known elements in the universe that make up all matter. And as of today, here in mid-November of 2020, there are 118 elements that have been discovered or synthesized, culminating with Oganesson, number 118. The periodic table has always kind of interested me because it's got a lot of rich history involved in it. Learn a little bit about mythology. The names of elements themselves come from a variety of places, and this is one of the really cool periodic tables that I've seen in recent years. It kind of goes over the different names of elements and where we get them from, whether they're a mineral or an astronomical body, whether they're from myth, named after a person or a place, or named after the properties they have. And it also kind of goes over some of their languages of origin. So this kind of explains partly why some of the symbols don't match up with the names themselves. This one is kind of interesting. Cobalt, element number 27, from the German word kobold, which means goblin. And the cobalt was a metal that, early people's thought would have been copper, but once it was going through the smelting process, it would produce compounds that contained arsenic. And so it was a little bit more of a, I guess, kind of like a tricky version of copper. They thought it was copper, but it was actually cobalt, very similar to it, but behaved differently once you started the smelting process, almost mischievously. So that's part of the reason why it has the word cobalt, based off of the German word kobold, which means goblin. Kind of like a tricky, mischievous, evil metal that's similar to copper. So that's where we get cobalt from. That's where it gets its name from. Another one that you might have noticed is kind of weird. Gold. Gold has the chemical symbol Au. Au for aurum, which is a Latin word for glow. Gold is a very shiny metal. It's ductile. It's flexible. You can make it into any sort of shape, which is why it's used a lot in jewelry. It's a precious, very expensive metal. And anyway, that's where we get the symbol Au from for gold. So periodic table is filled with all sorts of interesting tidbits of information that for those that like trivia, this is hours and hours of holes that you can and deep dives you can fall into just reading about this kind of stuff. But hey, that's not for everybody, but definitely for me. All right, so here is the periodic table of the elements that you're likely to see in your textbook. This table here is showing us all the different elements, and it's color coded, showing us the different groups of the periodic table. We're mostly going to be working in the groups 1 and 2, and then groups 13 to 18. Together, groups 1 and 2 and groups 13 to 18 make up what we call the main group, the main groups of elements. In the middle, there's this 2 sections. The first one that you see here, these are the transition metals. And then kind of shoved in here, kind of where you see these brown colors, are the lanthanide and actinide series. In reality, this table should actually be a lot longer, but if we were to try to fit in the lanthanides and actinides in here, this table wouldn't fit on the screen. All right, so let's move on to the next one. So the periodic table is organized into groups and periods. It's called the periodic table because when it was originally organized, chemists noticed that if you the properties of elements would show up periodically. Similar properties would show up periodically based on organizing the elements based on their atomic mass. So hence the periodic table, because these properties showed up with a certain frequency in a predictable period. So groups in the periodic table, groups correspond to vertical columns. So when I say something like groups 1 and 2 and groups 13, 18 are called the main group elements, I'm referring to the columns, those columns in the periodic table. A period is a horizontal row of elements on the periodic table. And they tend to go from metals to nonmetals. Nonmetals are kind of this green area to the right of this staircase, and metals are on the left-hand side of that staircase. Okay, over here, it's not as apparent here, the division, but you can see there's this bluish staircase. And those blue metals are what we call semi-metals, because they have properties, some properties of metals, but they also have some properties of non-metals. They're kind of in this transition area here between metals and non-metals. So metals are on this left side of the staircase. Metals tend to be shiny, malleable, and good conductors of heat and electricity. The bulk of the elements on the periodic table are metals. To the right of the staircase, we see non-metals, dull, brittle, poor conductors of heat, electricity. Some of them are solids, some of them are gases at room temperature. There's a liquid in there too with bromine. In and around this staircase, though, this bolded line, we see the semi-metals that have properties of non-metals and metals together. So boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Those are all the semi-metals. So reading the periodic table involves looking at each of the elements, and each element will have some information communicated about it. So this varies from periodic table to table. So most tables, though, will at least include the chemical name, and then they'll have a number, a whole number, which represents the atomic number. And the atomic number is equal to the number of protons contained in the nucleus of that element. So the atomic number is the number of protons. In an atom, a neutrally charged atom, okay, that number also corresponds to the number of electrons. The other big piece of information is the chemical symbol. So for oxygen, it's a capital O. That's what we call the chemical formula, or the chemical symbol. And then the last piece of information is usually going to be some decimal number, okay, which is the atomic mass. That's how heavy this an atom of this element is in atomic mass units. And this number corresponds to the number of protons plus the number of neutrons. So neutrons are another particle that can be found in the nucleus. They're neutrally charged, but they also contribute to the mass of the atom. This is a much more detailed part of the periodic table. This is for iron, and it's communicating a bunch of other information, things about charges, boiling point, melting point, some of its properties. The atomic mass here of iron is written as 55.85 atomic mass units. Now, some of you might be wondering, like, why does it have a decimal number at the end of it? Well, the decimal numbers are there because elements exist as a combination of isotopes. And isotopes are atoms of the same element, but they have differing numbers of neutrons. So here is the example of some carbon isotopes: carbon 12, carbon 13, and carbon 14. Carbon, most of the time, like almost 99% of carbon atoms, have 6 protons and 6 neutrons. About 1% of carbon atoms in a sample of carbon will have 7 neutrons. They'll have an extra neutron. It's still carbon, though, because they still have 6 protons. So as long as you have 6 protons, you're always carbon. What makes an isotope is a different number of neutrons. And the last one, the carbon 14, less than 0.1%, so one carbon atom in 1,000 will have 8 neutrons. And the reason we get those decimal numbers in the atomic mass is because the atomic mass is reflecting the percent relative abundance of these isotopes in a sample. So this has an atomic mass unit of 12. Carbon 13 will have an atomic mass unit of 13, and carbon 14 will have an atomic mass unit number of 14. So if you take all those numbers, those atomic mass units for each isotope, and multiply it by its percent relative abundance, and then you add all of those together, for carbon, you would get an atomic mass of 12.011, I believe. If you do the same procedure with iron, you would get 55.85. So that's where we get those decimal numbers from, and it's why it's not always a whole number. All right. So by now you've watched a few videos too, done some research on the development of the atomic theory. In one of the videos, one of the scientists that you looked at was Ernest Rutherford, and another one was Niels Bohr. Together, if you take their work together, we have something called a Bohr-Rutherford model. And Rutherford posited that every atom had a very dense, positive core called a nucleus, where there was a lot of positive charge in a very small volume right at the center of each atom. So that corresponds to the nucleus. He also posited that electrons were orbiting this nucleus, kind of like planets orbiting the sun. Niels Bohr, later on, theorized that the electrons were found in defined orbitals, and that the orbitals weren't just randomly located around the nucleus, but these orbitals had to be a certain distance from the nucleus, and there had to be a certain energy gap between the orbitals and the nucleus. And electrons could only be found in these predefined orbitals. So they weren't located kind of in, these orbitals weren't just randomly around the nucleus, okay? And the electrons could just fly around randomly. They had to be in these defined orbitals. So this is where we get the Bohr-Rutherford model. And for hydrogen, if we look at hydrogen's information on the periodic table, you'll notice it has 1 proton and 1 electron. It has an atomic mass of 1.01, which corresponds to its 1 proton. So this is the smallest element. It's very combustible, reacts easily with oxygen in what's called an exothermic reaction. If you draw its Bohr-Rutherford model, what you do is you draw the symbol right in the center to represent the nucleus, and then outside that, in the first ring, we would place its 1 electron. So there's the Bohr-Rutherford model for hydrogen. If we move left to right, the next element is helium. Helium has 2 protons and 2 electrons. Helium is an inert gas. It doesn't react with anything. And it's partly because helium has 2 electrons here in its first energy level. So Helium has 2 electrons first energy level, and that's all that can be held in that first energy level. If we increase an atomic number to element number 3, lithium, lithium is 3 protons and 3 electrons. According to the work of Niels Bohr, only 2 electrons can go in the first energy level. So the first energy level can only contain 2 electrons. If you have sorry, I was highlighting the wrong energy level there. The first energy level can only contain 2 electrons. If we need to place more electrons, they need to go into a second energy level. So lithium has 2 in the first energy level and 1 in a second energy level. If we move on to beryllium, beryllium has the atomic number of 4. 2 electrons go in its first energy level, and then 2 go in its second energy level. And then if we keep moving on down the periodic table, we get to element number 9, fluorine. Fluorine has 9 electrons. 2 have to go into its first energy level, and then 7 will go in its second energy level, like that. Neon, right beside fluorine, is element number 10 with an atomic number of 10. It has 2 electrons in its first energy level and then 8 electrons in its second energy level. Now, after neon, we have to go back to the left-hand side of the periodic table to find sodium. Sodium, now with 11 electrons, we don't place a 9th electron in the second energy level. Instead, that electron needs to be placed in the third energy level, because according to the work of Niels Bohr, 2 electrons go in the first energy level. The second energy level can hold a maximum of 8. The third energy level is where we now have to place supplemental electrons. So these are called Bohr-Rutherford models. Here's a summary of what we were just talking about. The first energy level can hold up to 2 electrons. And then the second and third energy levels can hold up to 8 electrons. Okay, and that's kind of what we're going to go with for our purposes, at least for the next little while. All right, that's it for this video about the periodic table and how to read the periodic table in order to draw Bohr-Rutherford models. I'll see you in the next video.